examine more closely how we get gravity out of the metric, the g mu nu. And so let's recall from last time, we discussed the geodesic equation and initially I'm going to be talking about massive particles. So I'm going to use the proper time along the geodesic. Remember from last time, if I'm discussing photons, I should instead use an affine parameter, which is only defined up to some scaling factor. So let's think about a massive particle. For which g mu nu dx mu d tau dx nu d tau is minus c squared. So this is following a time-like trajectory, and this is the definition of d tau. This is d tau is the proper time. You'll recall that gamma mu nu lambda is 1/2 g mu alpha g nu alpha lambda plus g lambda alpha nu minus g lambda nu alpha, which we derived from varying the action for the massive particle. And so what I want to show now is that if I make certain assumptions about this metric, that I will reproduce Newton's law for gravity, F equals ma, in a certain form. And we'll begin to derive the relationship between this description of gravity and Newton's. So let's consider a static gravitational field. Let's say metric, static metric. So d by dx naught equals 0. So I'm going to assume that this metric is completely independent of time. That's what we mean by static. And also I'm going to assume that g mu nu is equal to eta mu nu, the flat space-time metric, so it's nearly flat, plus a small correction, and the magnitude of that, the matrix elements of this small correction are all much less than 1. Yeah.
When you say partial S, you consider doing partial G?
Yes. In this, static means this in general, but yes. Okay, so this is a weak perturbation of flat space. It's flat space-time. Okay, so let's start off by looking at that. It follows from this, we're going to need the inverse metric as well in this formula. And it follows from this that the inverse of the metric is eta with upstairs indices minus h with upstairs indices. Okay, what does h with upstairs indices mean? It just means, so h mu nu means eta mu alpha, eta nu beta, h alpha beta. Okay, so I'm just using eta to raise and lower indices on h. And you can check that this is the inverse of that matrix to order h squared. Okay, because if I multiply these things, then I'm going to get g mu alpha, g alpha nu, right? So I multiply this guy by that guy. The eta with eta will give me delta mu nu. The eta with h will give me minus h mu nu. Okay, so that's taking this minus h and lowering its second index with eta. Likewise, taking this h and raising one of the indices gives me h mu nu plus order h squared. So this plus order h squared. And so that's approximately delta mu nu. That's equal to delta mu nu plus order h squared. No, there's a mu and a nu.
Oh, okay, I'm sorry. I'm looking at this wrong thing.
Okay. So that's the inverse metric. Roll it around once more so it's nearby. Okay, so we're ready to calculate gamma. Well, let's look at that equation. So the geodesic equation we want to make one more assumption. And we're going to assume that dx, the magnitude of dxi by dt is much less than c. Okay, so I'm making these three assumptions: a static metric, weak perturbation of flat space, and velocity of the particle being much less than the speed of light. Yeah, it seems reasonable. That's all the situations we're most familiar with. And then the geodesic equation simplifies. Becomes, so the spatial components d2xi d tau squared equal to minus gamma I. Now, if the spatial parts of the, so this of course implies that the xi d tau is much less than dt d tau. So when I look at the geodesic equation where I have the dxi d taus, I can just drop those terms compared to the dt d tau terms. So, or rather dct d tau, dct d tau. Okay, so these are the biggest terms in the equation. And we also have d2t d tau squared is equal to minus gamma 0, 0, 0, the same thing. But if we look at gamma 0, 0, 0, with all three indices 0, that inevitably involves a time derivative. Okay? The first two terms, you have the derivative with respect to the lower two indices. So if either one is 0, so both of them give 0, because both lower indices are 0. The upper index, if it's 0, then you see this gamma for weak fields, gamma nu lambda is approximately 1/2 eta mu alpha times h nu alpha lambda plus h lambda alpha nu minus h lambda nu comma alpha, right? Plus order h squared. Because you get something only of order h from the derivatives here, because eta is a constant matrix. And so if you took any more h's from here, it would be h squared. So, so by this argument, if the upper index is 0, then alpha must be 0. This derivative is 0. So this vanishes. Okay, so this is equal to 0. Okay, up to order h squared and dxi dtor squared. Okay, so we just have to analyze these two equations. Now, this equation implies that t is proportional to tau, because the second derivative of t vanishes. But if t is proportional to tau, then I can just, this d tau is a constant times dt, right? And so I can just cancel these two d taus here and divide by the t's, and I get, so let's call this 1, and let's call that 2. So equation 2 implies t is proportional to tau, so equation, therefore, 1 implies d2xi dt squared is equal to minus gamma I00 c squared, and gamma I00, if we work that out, so the upper index is I, these two are 0, so the first two terms vanish because they involve time derivatives. The last term, the upper index is I, these two indices are 0, so I get minus 1/2, which cancels the minus sign, so plus 1/2 h00 comma I times c squared. Okay, but this is just Newton's law for gravity. M d2xi dt squared equals the gravitational force, which is minus the gradient of the gravitational potential times the mass. Okay. And of course, the whole point of Einstein's realization is that the mass cancels in Newton's law, and somehow the particles respond, all particles, no matter what their mass, respond to the same thing. In this equation, that's built in. They all responding to the same space-time that they live in. And so from this, we can identify h naught naught is equal to minus 2 phi of x over c squared h naught naught of x. So the perturbation in the time component of the metric is just minus twice the gravitational potential over c squared. And if you think about dimensions, you know, gravitational potential is always something like gm over r. It's a gravitational potential. And dimensionally, one has that this gm over r it has dimensions of velocity squared. Right? You remember for circular orbits, for example, you get an equation like this. So phi has dimensions of velocity squared, so phi over c squared is dimensionless. Okay, so we shall see that Einstein's equations for G for G mu nu set del squared phi is equal to minus 4 pi g rho. I believe it's plus 4 pi g rho. Okay, which is Poisson's equations. And this rho is the density of mass. The density of mass. Okay, so that Poisson's equation is the analog of the equation for the electrostatic potential in electrostatics. And if you solve this equation for a point mass, you will, or any spherical mass, you'll discover that phi goes like minus g times the total mass over r. Okay, so we haven't done that yet, but that's just looking forward. All we've done so far is to figure out what the 0, 0 component of the metric means in Newtonian terms. Yeah.
So I can see why the mass cancels out in the law for gravity, but it still seems weird to me because any mass we choose is going to warp space-time itself, right? So
yeah, this is all ignoring that effect. So this is the geodesic equation describes a test mass that propagates through space-time and doesn't distort space-time at all. That's all it does. Okay? So it applies to a small particle. If you ask what is the influence of that particle on space-time, if the mass is small, the influence is small.
right.
Just when the equation you framed on the
It's not actually the mass. In fact, there's a slightly more subtle question. The influence of that particle on space-time is in fact determined by the perturbation it makes to the metric, which is a dimensionless number. And so when you take a particle, so imagine I took a little ball, and I said, how much is that ball going to distort space-time? Well, the distortion is the dimensionless deviation from flat, okay, which is the gravitational potential on the surface, okay, which would be minus gm over a, okay, and then I divide by c squared. Okay, so if I pretend particles are little balls, this would be the distortion of space-time that they cause, the dimensionless. And as long as that number is small. So it depends on both their radius. They better not be too tiny. Otherwise, they'd make a black hole.
Right.
And then you'd be talking about the propagation of a black hole through space-time. And that's a pretty nonlinear phenomenon. Okay? Nevertheless, black holes actually do follow geodesics. People have spent many decades proving this. But they end up following geodesics, but that's certainly not obvious. Any other
I figured it out.
Okay. So, okay, we've just made this limited step of seeing what h naught naught is. So for a point mass, well, let's not talk, let's say a mass m, okay, and I'm going to treat it as a little ball of some radius. So phi would be minus gm over r. This is, of course, outside the mass. And so what we learn is that g naught naught is approximately minus 1 minus 2 gm over r c squared. And of course, the calculation's only, the inference is only valid when this number is small. Nevertheless, it's tempting just to extrapolate to when it's large. And the deviation from minus 1 is of the following magnitude: 10 to the minus 9 at the surface of the Earth. Okay, so the space-time metric we live in is 1 part in a billion away from being flat space. It's 10 to the minus 6 at the surface of the Sun. It's 10 to the minus 4 at the surface of a white dwarf. It's a certain kind of compact star. It's 10 to the minus 1 at the surface of a neutron star. Okay, so that's a star that has collapsed to a degenerate Fermi gas. Consists of mostly neutrons. And let me just put that up a bit. And this deviation, of course, is 1 at the surface of a black hole. In fact, that's the definition of the surface of a black hole, where g naught naught in a certain coordinate system vanishes. It's called a horizon. So something pretty dramatic happens there, which we'll study in detail next week. Okay, but this is a start. In fact, this line of argument, I have to tell you something amusing, which is with this line of argument told Einstein what g naught naught is. Okay, so Einstein said, okay, great, let me calculate the deflection of light by the sun. I know what g naught naught is. And he worked out the geodesic equation for a photon, for a massless particle around the sun. And he only included this term. And he got a result which is wrong, okay, by a factor of 2. Because he forgot about the Gij. So it turns out the Gij gets disturbed by exactly the same amount. And if you put both factors in, you get the correct deflection of light. We will do that later. So another mistake, but not a very serious one. So now let us discuss. So that's the most direct effect of the metric in bending trajectories. There are some other surprising results. Again, well, the one that is most directly related to this is called gravitational time dilation. As I explained to you before, if you want to stay young, you have to move fast. It turns out if you want to stay young, it's best to be in the strongest gravitational field you can find. And then your clock goes much more slowly than everyone else. Yeah.
flatness for G00, isn't
Yes.
that a gauge-dependent quantity? For
Yes, it is. In
for the-
fact, G mu nu is a
Right.
gauge-dependent quantity. The metric is not gauge independent.
But for the weak field cases, we can just choose the gauge in which the metric looks as close as possible to flat. But
I've kind of implicitly chosen a gauge by assuming the velocities are small, things are independent of time, the metric is small.
There's only one mode in the perturbation.
I haven't, pardon?
There's only one mode of the perturbations you're considering here, which is the scalar ones. Responsible for deviation of light.
Yes, I mean, as soon as you set the time derivatives to 0, all the other things are going to go away.
So that's why.
So basically, there are also gravitational waves.
Yeah.
When I set all the time derivatives to 0, these are 0.
So that's the only surviving mode.
It's the only surviving mode, and it's tied to the matter. So just postpone the question.
okay.
All right? This is like a very naive first step. Okay? In general, the metric depends on the coordinates. And so obviously, implicitly, I've picked some kind of coordinates. I've picked coordinates which are flat, which are near flat space, and I've picked coordinates in which the metric is static. So I'm not allowed to change my time coordinates. You might worry I could still change my space coordinates, but you see, again, yeah, I mean, I haven't considered anything that depends on the space coordinates, so that's all happening at higher order in V over C or powers of H. Okay, so gravitational time dilation. The idea is, again, consider a static metric. Okay, and we're going to have a clock. This is the world line of a clock in some region where the metric is where the metric perturbation is non-zero. Okay, some perturbed region. Right, so G mu nu is not equal to eta mu nu. And then this clock is going to send out pulses. Okay, so here's a pulse. So by the way, this is t. This is ct, and that's x. The clock is going to send out a pulse at the speed of light, or a set of pulses, okay, at the speed of light. And then somebody over here, where there's no metric perturbation, G mu nu equals eta mu nu, or it's approximately eta mu nu. And there's going to be another clock here. And this other clock is going to detect those pulses. Okay, so this clock, the ticks of this clock are going to correspond to measured arrival times of light rays at the other clock. Okay, so it turns out it's very easy to infer the relationship between the ticks of the clock here and the measured difference in time, arrival times between these pulses. So the clock so by the equivalence principle, remember the laws of physics in the presence of a gravitational field are obtained just by substituting eta for g, or g for eta. Wherever we see eta, we put g. And the clock, and locally, we can pick space-time coordinates in which g equals eta. So the clock has ticks which, so it ticks at, ticks are separated by delta tau. Okay, and delta tau is the space-time interval between those ticks. Delta tau is the time between ticks in a frame in which the clock is stationary, because obviously if it's moving, you get time dilation. So we can write that down as follows. Delta tau is minus g mu nu dx mu dx nu to the 1/2. Okay, so here's an expression which certainly by choosing coordinates, I can make g equals to eta. In those coordinates, the clock should just obey the laws of mechanics as described in flat space-time. Gravity has no influence at all. Okay, so we can first pick g equal to eta. And then we know we can ask the manufacturer, what's the time between the clocks? When you weren't in a gravitational field, it should be the correct answer. And second of all, we can pick a Lorentz frame, pick a local inertial frame. Sorry, pick a Lorentz frame in which the clock is static. It's static. Okay, and in that frame, delta tau, I'm always getting these c's wrong. This would be 1 over c, would be equal to delta t. Okay, so this expression equals the time interval between ticks of the clock, and because it is invariant under general coordinate transformations, it's equal to the same time interval in any coordinate system. Okay, so now all we have to do is let us evaluate this. So the right-hand side is coordinate invariant. Let us evaluate it in a coordinate system in which g mu nu is static, independent of time, and g mu nu is approximately eta mu nu at large distances from large distances. Okay, so there's some local gravitational field, for example, due to a star. But over here, there's no gravitational field. We're a long way away from the star. So that defines a coordinate system. Let's pick that coordinate system in which, and we'll call this, the time in this coordinate system is called t. In this coordinate system. Is t. So it follows. Now you see, in that coordinate system, I want to know how far apart. So I picked this coordinate system. It's valid for all of space, okay, but it was defined by its properties out here. In that coordinate system, it must be that, since the metric is static, it must be that the time separation between the ticks of the clock in that coordinate system, okay, which will be delta t. Let me just, I don't want to confuse it with this one. So this is delta t in this. Let me just say it this way. Okay, the clock ticks are delta tau apart in these coordinates. Okay, so those coordinates are the ones in which g is eta at the clock and there's a local Lorentz frame in the rest frame of the clock. We're picking another coordinate system now. This is a global coordinate system whose time is t, where the metric is flat space at large distances, but the metric's certainly not flat space over here. Nevertheless, because the whole setup is static, if the clock ticks are separated by delta t in this coordinate system over here, they must be separated by delta t over there. Okay, because this tick and this light ray is just transported up by delta t in this system. There's nothing else going on in t. Okay, so delta t here equals delta t there. So what we have to do is use these two equations. From this equation star, delta tau, this is the ticks of the clock in the absence of gravity in its rest frame. This is equal to 1 over c minus g naught naught delta t squared, and to the half. In other words, delta t is equal to delta tau, and of course this is a c squared in there too, which cancels here. Delta t is delta tau over root minus g naught naught. And this is x clock at the position of the clock. Okay, so in other words, the time interval between ticks as measured by somebody at infinity equals the time interval that the clock manufacturers prescribe. They manufactured it in the absence of gravity, multiplied by this factor, which is greater than 1. Okay, so this is greater than delta tau. So in other words, so that's why it's called time dilation. So you will see a larger interval at infinity between the ticks of the clock than somebody does who's sitting in the gravitational field. And so, for example, just from these numbers here, the time dilation effect at the surface of the sun is 1 part in a million. Yes?
Am I right to assume that if we think of the perturbed region as abruptly ending, it's like in the two...
No, it doesn't have to be abruptly.
Yeah, but yeah. If I do assume that, is it true that the light rays are reflected and the...
The direction may change, yes, sure. I mean, there's nothing... we're just in some coordinates, t and x, and nothing particularly special about those coordinates. So these will bend, you know, they don't have to go at the speed of light in those coordinates. They don't have to go at 45 degrees in those coordinates. No. So the light rays are deflected in those coordinates. But since the whole thing is independent of t, every light ray is going to be deflected in exactly the same way.
Yes.
Yeah. And that's all you need for this argument, is that the interval in time over there is the same as the interval in time over here in this coordinate system where the metric is static. Okay, and then you say, but the interval in time over here isn't actually the proper time measured by the clock. But the proper clock is measuring this, you know, clock measures this time, delta tau. Clock measures the time which is fixed in a coordinate system where the metric is flat. It's a different coordinate system. And so this transformation between the two coordinate systems is what gives you the effect. So there's a frequency shift in atomic lines, emission lines, which is of order 1 part in a million for atoms on the surface of the sun. On the surface of the sun. And this is now quite easily measurable. In fact, the most accurate experiments measuring gravitational time dilation. There was a very famous experiment at Harvard where they used the physics building, and they used the Mossbauer effect, which is a very precise way to detect tiny shifts in radiation frequencies. So they had a source at the bottom of the building shining up to the top of the building, and it was exactly the situation. And they confirmed the effect. I can't remember how accurate. They confirmed the effect to they confirmed it to about 1%. So this is a shift in frequency over frequency, and given at the surface of the Earth, it's about a part in a billion to a few percent. And then later on, Vesso et al. Used masers on satellite and Earth. So they used the Earth's gravitational field and then a maser in space shined down to the lab and was compared with a laser in the lab. And they measured the same thing to confirmed GR2 around 2 times 10 to the minus 4. And people, I mean, obviously with the amount of data coming in from astronomy these days, there are always new opportunities for checking this. The most recently, pulsar timing provides an incredibly precise way of checking all these predictions of GR. And I believe it's a little bit better than that. It's about a factor of 10 better than that. And actually, Avery Broderick, who works here, is one of the world's leaders at trying to observe black holes through exactly this effect. That the black hole is surrounded by a cloud of gas. Well, it's through this and other effects, but this is a contribution. Black hole is surrounded by a cloud of gas. If you see the gas radiating from nearby to the black hole, it looks much redder. The wavelengths coming out are much longer than they would have been if there was no gravity. And so basically you see a patch of the sky which is radiating less intensely and at longer wavelengths than the region around it. And it seems that within a few years, using very large baseline interferometry, which is what he uses, it's radio telescopes, which are all around the world, used as a single interferometer, you will be able to get maps with a resolution equal to the size of the black hole in the center of our galaxy, and literally see the black hole through this effect. Okay, so now we'll continue with a little mathematical interlude. I've tried to minimize the maths but I better say a little more. And so let me just say something about tensors and covariant derivatives. So we've already said that G mu nu is the line element, or defines the line element on spacetime. Okay, it's what we use to measure distances. I haven't really talked much about what the picture of spacetime is and what the geometry of spacetime is. So let me give you an example, just to think about. Example of a curved space, a sphere. So this is maybe the simplest example of a curved space. And we'll see the various issues that arise when describing the sphere with a metric. So sphere is a particularly easy case. Let's take 3 dimensions, x1, x2, x3, and consider the subspace x1 squared plus x2 squared plus x3 squared equals 1. This is a 2-dimensional sphere, and of course it looks like that. We want to describe something. We want to describe the geometry of this 2-dimensional sphere, preferably without referring to the space it is embedded in, which is in this case 3-dimensional flat space. So one way to describe that, so coordinates on S2 are, for example, e.g. polars, spherical polars. And we have, of course, x1 is sine theta cos phi, x2 is sine theta sine phi, and x3 is cos theta. Okay, so all we've done is solve this constraint by re-expressing x1, 2, and 3 in terms of 2 coordinates. And then the constraint is automatically satisfied. Theta, you can see what theta is. Theta is this polar angle. Phi, yeah, maybe let me draw it on that picture. I'm sure you know this very well. If we take some point on the sphere, then this is the polar angle. And if I drop a perpendicular to the x1, x2 plane, this angle is phi. So the metric, the line element, okay, which is given by the metric, is just the line element in flat space, but when I insist that the coordinates are on the sphere. Okay, constrained by the requirement that x1 squared plus x2 squared plus x3 squared equals 1. So we say that the line element on the sphere is just inherited from the line element in flat space that the sphere is embedded in. And if I substitute these formulae in here, you will find this is nothing but d theta squared plus sine squared theta d phi squared. And so it's not, the sphere is not flat, it's curved, and the curvature is encoded in that element. So these coordinates or another way of saying it is that G mu nu is the 2 by 2 matrix, which is 1 sine squared theta 0, 0. And you can calculate the connection and the curvature and everything for the sphere as a good exercise. Now, these coordinates have a problem. Can anyone tell me what the problem is? Remember, the basic idea is that the basic idea in describing a curved space is that locally, it is always possible to choose coordinates in which it looks like flat space. Okay? But generally what happens is that the coordinates have a problem somewhere on the space. There's no requirement that a single coordinate system covers the whole space. Okay? That is the whole idea of a coordinate system that is a coordinate system is something which is local. That I can pick coordinates in which the metric is flat locally. Now these coordinates, anyone tell me what's wrong with polar coordinates? Pardon? Singular. They are singular at the poles, yeah? Are singular at the poles. Why is that? Because the pole is obviously one point, yet it's described by theta equals 0 and arbitrary phi. You see, this theta ranges over 0 to pi. This is the North Pole. Sorry, this is the South Pole. This is the North Pole. And phi ranges over 0 and 2 pi, with 2 pi identified with 0. Okay, because phi is a coordinate on a circle, so 2 pi should be identified with 0. Theta ranges from 0 to pi, identified. Okay, but now you'd say that the North Pole is theta equals 0 with arbitrary phi. So one point with an infinite number of possible coordinates for that point. So something's obviously wrong at the poles. The relationship between points and coordinates breaks down. A good coordinate system is one where each point is described by a single set of coordinates. Now, it's not difficult to pick better coordinates, but as I said, you shouldn't expect that one coordinate system will cover the whole space. So it turns out that for a sphere, you can do no better than find two sets of coordinates which together cover the space in a non-singular way. So better coordinates which are one-to-one for which are for almost all. I'll say that. Let me just say they're better for now. I'll describe exactly how they're better. Now, better coordinates are as follows. So imagine I consider a plane through the sphere. Okay, and let's consider some point which lies on the sphere. Now shine a light ray from the North Pole through the point to hit the plane. Okay, so this is the x1, x2 plane. This is, of course, x3. Here's my point. And this I'll call the coordinate. Okay, so these are called projective coordinates because you project projective coordinates. And so you need to project from somewhere. So the North Pole projective coordinates are defined as follows, that x1n, x2n, so they're just, every point has two coordinates, x1n and x2n, and this is equal to x1, the coordinates in 3D, over 1 minus x3, x2 over 1 minus x3. And just to show you that from the picture, this length here is, of course, the radius is 1 of the sphere. So this let me draw this diagram. So this, the height of the point is x3. This distance is 1 minus x3. And so it follows that this coordinate x1 is equal to x1n. Sorry. This is x1 as well. That is x1. So by similar triangles, this is x1. So by similar triangles, this triangle is similar to that triangle. So what you see is that x1 over 1 minus x3 is equal to x1n over 1. Okay, so this distance is x1n. x1n. Okay, so these are North Pole projective coordinates. And then South Pole projective coordinates are defined exactly the same way. x1s, x2s, but by projecting from the South Pole. And so you just replace the 1 minus x3 with 1 plus x3. And so what you're doing is mapping every point on the sphere to a point on a plane. x1n and x2n go from minus infinity or s. Go from minus infinity to infinity. Okay, so the sphere gets mapped to the plane.
The second South Pole coordinate's got needs x2 and x1.
Oh, thanks. Now, so basically, so can you tell me where is the North Pole projective coordinate system singular? It's singular somewhere at the North Pole, right? Because if I'm sitting at the North Pole and I project some point which is very near me onto this plane, it's going to be out at infinity. All right, so then these are singular at the North Pole. At the North Pole. And these ones are singular at the South Pole. At the South Pole. Okay, but they are one-to-one, but they are regular and one-to-one everywhere else. Okay, so apart from those 2 points, they're very good coordinate systems because every point on the sphere has a unique point on the plane. So the best we can do, so if you like, the best we can do is to cover the sphere with the North Pole coordinates, which cover it everywhere apart from the vicinity of the North Pole, and the South Pole coordinates, which cover it everywhere apart from the vicinity of the South Pole. But you see, they overlap everywhere in between. So they're equally good coordinates everywhere in between. And we can even work out the transformation between them. Is good everywhere except the poles, okay, where one or other of them break down. And so, for example, you can see that x1n is x1s over x1s squared plus x2s squared, and x2n is equal to x2n over x1n squared plus x2n squared. So I'll leave it to you to check that. These are called the transition functions. Okay, because they enable you to make the transition from one coordinate system to the other. And like you can, of course, express the metric in terms of either of these coordinate systems. And the metric, or the line element, ds squared is equal to 4 dx1n squared plus dx2n squared over 1 plus x1n squared plus x2n squared. And similarly, for x s coordinates. Okay, so the metric takes the same form in both the north and the south coordinates. Just looks like that. I should have another square there. For example, you can check via noticing that the relationship between the north pole and usual spherical polars is cot theta over 2 cos phi, and x2n is cot theta over 2 sine phi. And then using all the trigonometric identities. Okay, so that's an example of what's called a manifold, a geometrical manifold with a metric. And these are different coordinate systems you can use. Any one of them is equally valid, but all of them have problems somewhere. And then the general idea in differential geometry is to show that, so it's sort of a strange thing. We have this conception of an object, right, which is a sphere. We don't know how to describe a sphere without mentioning coordinates. Okay, we have a mental picture of it, but there's nothing we can do to describe it apart from introducing coordinates. But when we introduce the coordinates, we know they're meaningless. Okay? Because no one set of coordinates is preferred to any other set of coordinates. They're just completely arbitrary. I can draw a line, I can draw a grid on the sphere however I like, and they're all equally valid. Okay? So this is an example of the fact, it happens many times in physics, that we have to introduce variables which are redundant, often hugely redundant, okay? Like in gauge theory, the gauge field is redundant. And so we're sort of grasping at something which is beyond our description on its own terms, Okay, we think this geometry exists. We can't describe it except introducing numbers, and then those numbers are hugely redundant. So we always have to have this picture that we're describing something which equals a set of numbers modulo some big symmetry between those sets of numbers. So essentially the picture is this. We have some coordinate system, x. So we have, so in general, we have many coordinate system, have an infinite number of coordinate systems. And we have to check that that everything we do is equivalently described by all of them, by any of them. Okay, so we have a coordinate system x, and then we might make a coordinate transformation to some coordinate system x prime, or we might make some other coordinate system to some other transformation to some other coordinate system x double prime, okay, or we might relate x prime to x double prime. And in fact, the most important consistency check in Riemannian geometry, when you introduce connections and so on, is to check that doing this gives the same result as going straight there. If that is true, then you're guaranteed that whatever coordinate system you do, they're all equivalent. Okay, so there's sort of a network of coordinate systems, each one equivalent to every other, and you can deform any path in this network to any other path in the network. And you need, i.e., we need x double prime of x to equal to x double prime of x prime of x. And we also need the derivatives to satisfy this. I mean, all geometrical objects we construct should be should satisfy that property. Okay, so let me now talk about, oh, I've left that. Let me now talk about tensors. Okay, so tensors are objects like this, whose actual value in any coordinate system doesn't mean anything, okay, on its own, okay, because you can transform them to any other coordinate system. But they're objects which live on this curved manifold. So the simplest tensors are scalars. Okay, and these are the only ones whose value actually does mean something. Okay, so the transformation law is that phi prime of x prime equals phi of x. Okay, so just think about that for a moment. What is a scalar? Well, it's a function which lives on the space. So every point of this curved manifold, say a sphere, there would be a definite value of phi. Okay? Then if phi is a scalar, the definition of phi in the new coordinate system is that the value of the function phi prime at the same point, okay, this is x goes to x prime. This is the same point in the new coordinate system. The value should be the same. Okay, i.e. the value at i.e. the same point gives you the same value. Okay, same point does not mean same coordinates. Okay, the same point has totally different coordinates in the two coordinate systems. But if the coordinates are x in one coordinate system, they are x prime in the other coordinate system. Then we have vectors, and we have two types of vectors which have upper indices. These are called contravariant vectors, and the way I remember that is that TR is short for trees, and trees go upwards. Okay. Covariant indices, valley is short for valleys, and valleys go downwards. I don't know what the original motivation was, but there are two types of vectors, and they transform as follows: that v prime mu of x prime is dx prime mu dx alpha v alpha of x, and covariant vectors, v prime with the lower index, transforms with the inverse transformation matrix, dx prime mu dx alpha v alpha of x. And we've already seen examples of both of these. Contravariant vector is dx d lambda, the tangent vector to a curve. A covariant vector is the derivative. And of course, we've already seen tensors with more indices, like f mu nu. And it's easy to understand that there would be tensors with any number of indices. So higher valence tensors. Valence means the number of indices of each type. So e.g., T mu nu lambda alpha beta has valence 3, 2. That just means 3 upstairs and 2 downstairs. And then there's some general rules for getting tensors from tensors. You can add two tensors, a mu nu plus b mu nu. That's still a tensor. You can multiply. So we can add, we can multiply. We can write a mu nu b alpha beta. That's still a tensor. We can contract indices. Okay, so this is obviously a 1, 1 tensor. This one would be a 2, 2. This a mu nu b mu alpha would be 1, 1 again. We lose 1 up and 1 down when we contract. And and so on. Okay, and the basic properties of a tensor is just that it transforms according to the transformation matrices, right? So T prime of x prime would be dx prime, dx prime, dx prime, dx, dx, dx for the upper indices, and then dx, dx prime, dx, dx prime for the lower indices times t, and I won't bother filling in all the indices. Yeah.
Now, when you've written out t, you've written the lower indices directly on the upper indices.
I've written
The lower indices directly on the upper indices.
these ones.
Yeah.
They're just different. You can be careful which order you place them in. Okay. So you can do this, if you like, or any variation. And what that's sort of telling you is that you're leaving a space there because you might raise this guy.
Yeah.
And if you raise it, then you might define this to be G alpha gamma, the other one, nu gamma, nu beta lambda. So depending on the context, you may want to keep track of where the positions are. If you just define them with up and low and you're never going to move them up and down, there's no point in ordering them this way. There's only a point in ordering them if you're going to shift them up and down.
Second question. So if I'm trying to think about a scalar, then this one, the one I'd probably pick would be the electromagnetic potential.
It's not a scalar.
Of 5. Oh, it's not a scalar.
No. We showed that before, right? Because A mu, the vector potential, was the electromagnetic potential times AI. So phi is actually the zero component of a 4 vector. It comes along with this magnetic vector potential. So I don't think we've had a scalar so far. There've been no scalars so far.
What about the retraction of G with its like
The proper time is
Yes, that's true. Proper time is a scalar. Yeah, you're right. That's the only scalar we've had. Yeah, that's a scalar.
Mass and charge.
Pardon?
Mass and charge. Charge.
Mass and charge are scalars. I guess that's true. Yeah, M and Q, they don't change. But they're not functions of
space
point either. And even this is only a function along a curve. It's not really a space-time point. We're going to get a scalar very shortly. Okay, so don't worry. Scalars are coming. And then we've already seen something we call covariant derivative. So this is another way of getting tensors from tensors, is you can differentiate tensors. I've already discussed how when we varied the particle action, we got a connection. And I emphasized that the role of the connection was to make the geodesic equation generally covariant, to make it valid in all coordinate system, right? Because the d2x d tau squared did not transform like a 4 vector. The gamma came in and compensated it. Transformation of gamma compensated for it to make a 4 vector. So it shouldn't be a surprise that when we take derivatives of tensors, they are not tensors. Ordinary derivatives are not tensors. That's kind of obvious, right? Because the tensor transforms with all those dx dx's, right? If I differentiate it, I'm going to get d2x dx. That's the wrong thing. So I've got to cancel the d2x dx. And the way I do it is by defining this covariant derivative. So we'll call it like this instead of d mu. And this covariant derivative of some tensor, let's just do an example, with one up index and one down index. I'll just do dots in case there are other indices. And this is defined to be the ordinary derivative and then for for a tensor index which is raised, I add a gamma, which is raised. Okay. Now, the nice way to remember how to include the gammas, okay, is, and this is sort of a very general way, is that the derivative index is the last index of the gamma, downstairs, because this is downstairs. Okay. And then everything else will take care of itself, because obviously I have to have an index up. This is a tensor with up, so I better have this guy up. I've got to contract it with my A. So this is going to be gamma, gamma, beta. Okay, so basically I'm just taking this upper index, contracting it with my connection, and then the connection, it transforms it back to an upper index. And the connection has this index for the partial derivative as well. For lower indices, you've got to include a minus sign. And again, that's not too surprising. The lower indices transform with the inverse coordinate transformation matrix. And again, last time I gave you an argument that the second derivative of the upper guy was related to minus the second derivative of the lower guy because of the basic identity that dx, dx prime, dx is equal to 1. Okay, and if I differentiate that again, what I get is the sum of the second derivatives of dx, dx prime, and dx prime dx have to be 0. So that results in this minus sign. So again, we put the derivative index down, but now I've got to convert a down index to a down index. So gamma does that. Again, so I contract the down index, leave the up index alone, and etc. Okay, i.e. 1 gamma for each index plus for upper minus for lower. Okay, and then the statement is that the covariant derivative is a tensor. Of a tensor is a tensor. But you see, because it's a tensor, you can evaluate it in any coordinate system. So now there's a very useful statement. If a tensor is 0, in any coordinate system, it is 0 in all coordinate systems. No. Yes. Let's say in any one coordinate system. Okay, so in other words, so if a tensor is 0 everywhere, in any one coordinate system, then it is 0 everywhere in any coordinate system. Sorry? Oh, it does hold at a point, but it's just the statement I'm making is a different one. I'm just saying that if a tensor is 0 in one coordinate system everywhere, then it's 0 in all coordinate systems everywhere. So an example is the covariant derivative of the metric. Okay, so that's a tensor, but I already showed you that there exists a coordinate system in which the derivative of the metric is 0, and the connection is expressed in terms of derivatives of the metric. So the connection is 0. This derivative is 0. So this is 0 in locally flat coordinates. So it must be 0 in all coordinate systems. Okay, so you can often get away with making arguments like that and doing no calculations at all. Of course, you can check it also. So let's just work it out. This is equal to d mu g alpha beta. Now I've got two lower indices, so gamma mu alpha g gamma nu minus gamma nu alpha g mu gamma. This is equal to g, what have I done here? Alpha mu nu. Sorry, I've changed my indices around. D alpha g mu nu is this guy. Okay, that's the covariant derivative. So this is g mu nu comma alpha. Comma alpha is the same as d by dx alpha. These g's lower the index on gamma. If you remember the definition of gamma, mu alpha was 1/2 g gamma beta g mu beta alpha plus g alpha beta mu minus g. So these g's just remove the g with upstairs indices. They change it to a delta, and then the delta forces the appropriate index to be nu. And so this is 1/2 g mu nu comma alpha plus g alpha nu comma mu minus g mu alpha comma nu minus 1/2 g nu mu comma alpha plus g alpha mu comma nu minus g nu alpha comma mu. Okay, so I just worked out the three terms. And I should have had minus sign here. Okay, and so what you see is that these first two terms cancel this guy, and then this one cancels this, and this one cancels this. Okay, so the sum is 0. Yeah.
This proof holds for any kind of coordinate system.
Yes.
Okay.
Yes. Just from here. We've already showed that I can pick coordinates in which this is 0. Those were the locally flat coordinates. It follows without any further calculation that this must be true in any coordinates because it's a tensor. So this object in any other coordinate system, prime, okay, is just given by dx, dx prime, dx, dx prime, dx, dx prime of the same thing in the non-prime coordinate system, but that was 0. So this must be 0.
I mean, the calculation you have just done holds for any.
Yes, I've also. This is just
so
doing it
they are just
explicitly. They're equivalent.
Okay.
Yeah, I'm just checking this. Okay, so that was a general argument. I'm just checking that it's indeed true. It better be true, otherwise my whole understanding is messed up. Okay. Okay, so let me just say a little bit about what we'll do next time. So this time we've we've made tensors by differentiating tensors. And this turns out to be the most efficient way to construct the Riemann tensor, which measures the curvature of space-time. You see, the basic property of derivatives of ordinary derivatives, so whereas these things always commute, it doesn't matter which order you do partial derivatives, you get the same answer. Whereas partial derivatives commute, it turns out that these covariant derivatives do not commute. Okay, and in particular, if I work them out on a vector minus d nu d mu s rho. Okay, so if I work out the commutator of two covariant derivatives acting on a vector, then it gives me a non-zero tensor. And furthermore, that tensor is linear in S and does not involve any derivatives of S. So it turns out it gives this very special tensor S sigma, okay, for any four vector S rho. And this guy is the Riemann tensor. Okay. It turns out this Riemann tensor depends on second derivatives of the metric. And if you remember, there was a certain number of these second derivatives we could not set zero. And they're exactly the same as the number of components of this tensor. So next time we'll construct that tensor explicitly. And once we've done that, we'll be ready to write down the Einstein equations, which will be the equations for the second derivatives of the metric in terms of the stress energy tensor of the matter. Now, is there a tutorial this afternoon? What's that? Oh, the twins. Okay, fine. I thought, pardon?
The twins are back.
Twins are back. I thought we were doing time dilation.
Right.
Okay. Oh, twins in time. The twins come back for more time dilation. Yes, that's right. That's right. Okay, any other questions? Yeah.
In the example you gave of covariant vector, you wrote
Yes.
the derivative,
Yeah.
partial alpha.
Yeah.
But I thought the derivative was not a tensor. The partial derivative.
Oh, yes.
You raised it already.
I raised it already. Okay, so we do have this formula. This is a sort of formal thing. I haven't said what it's acting on yet, okay? So this is true as an identity, right? dx alpha d by dx beta. Okay, so that's true as an identity, that if I take the ordinary partial derivative, it, just by the chain rule, if I have a function of x prime, so f of x prime, and then if I consider x prime to be a function of x, I should differentiate with respect to the x, and then, I think I've said it the wrong way around. F of yes. F of x prime. That's right. So first I differentiate with respect to x, and then I differentiate x with respect to x prime. So that is an identity. This, of course, doesn't, this doesn't live it's not a tensor. D by dx isn't a tensor. It's not a quantity which lives on the manifold. You can define it to be in a certain way. But let's just say the following, that if I have a scalar, d by, maybe that's the simplest example. So if I have a scalar, which has a value at every point, this is a vector. Okay? And actually, this equals to the covariant derivative of the scalar, because the rule is to add a gamma for every index, and this has no indices, so no gammas. Okay? But if I now try to do this, that is not a tensor. Now, why is it not a tensor? Well, this part of the calculation is valid. Okay, so let's put the primes in. So this is valid. It's equal to dx prime alpha x mu d by dx mu. This guy is not equal, right? This one is dx prime beta dx mu v mu. Okay, and if I've got that right, yes. So it's almost working, but the problem is this derivative acts on the transformation of the vector. So so you're right that I can't really think of this d by dx as a vector unless it's acting on a scalar. Okay. If it's acting on a vector, then I've got to worry about its effect on this transformation matrix. Any other questions? No? Okay, so see you this afternoon.